In this video, we're going to talk about critical points. So let's start by reviewing some of our terminology from our first calculus course. I'm just going to draw a curve here so that we can label some of our critical points. Okay, let's say we've got a curve that looks like that. So this point is higher than all the points around it. So informally, you could say it's a hilltop. Proper terminology, either called a local or relative max. So let's go with the shorter name and just call it a local max. Similarly, this point here, lower than all the points around it. Informally, you could say it's a valley, but in proper terminology, we'd say that's a local min. Local minimum, local maximum are those 2 points. All right, now let's look at this point here. This point is certainly a local maximum, but it's also the absolute highest point on this curve. So that makes it both a local max and an absolute max. Whereas this point over here was a local max, but not an absolute max. And then this fourth point over here to the right, we could say that's definitely a local min. So I just say min for short, local minimum, but it's also the absolute minimum. So hopefully that terminology is familiar to you from your first calculus course, and we're going to build on that from there and look at critical points on multivariable functions. So let's recall from one of our previous videos on tangent planes that we were able to identify the points where the tangent plane is horizontal. We said that a tangent plane is horizontal when both z sub x and z sub y equals 0. So that fact is going to motivate us to define critical points in a moment, critical points for multivariable functions, and then we'll be able to draw a picture from there. So let's look at a definition now for critical points of multivariable functions. Points where z sub x and z sub y are both 0 or undefined are called critical points. Just a couple comments about this definition before we draw a picture. So first of all, you could have, for example, z sub x equals 0 and z sub y undefined, or vice versa. So you need both z sub x and z sub y to be either 0 or undefined, but they don't have to both be 0 or both be undefined. So that's the first subtlety of the definition. And then once we've got these critical points, we still need further investigation to figure out what type of critical point they might be. The options are the points could be a local maximum, they could be a local minimum, they could be a saddle point. So we'll draw a picture to see what that looks like, or it could be none of the above. So let's say that we've got a surface like this sitting in three-dimensional space. There are a few points I want to identify on here, which would be critical points for this multivariable function. So one of them would be right around here. One would be right around here. One would be right around here, and then there's something else interesting going on maybe around here. Okay, so this point on the left, that would be a local maximum. This one over here, also local maximum. Down at the bottom here, we've got a local minimum. So when we say something like local minimum for a multivariable function, again, we're just saying it's a point that is lower than all the other points surrounding it. Similarly, a local max higher than all the other points, all the other nearby points. Okay, now this point in the middle near the top of the surface is the most interesting one. There are really two vantage points when looking at this point. So we could be traveling along in this direction here. I'm just going to label this in blue. If we were taking that path through that point, we would say this point looks like a local minimum. But on the other hand, we could be traveling in a different direction along the surface. We could be climbing up the surface like this, coming up to that point, and then we'd be dropping down on the other side. So from one direction, it looks like a local minimum, from the other direction, it looks like a local maximum. And so when you have that behavior, we call that a saddle point. So the behavior of critical points is a little bit more complicated when we're talking about multivariable functions. We not only have local maximum and local minimum points, but we also have these saddle points. It's also possible that when you identify a critical point that it falls into none of these categories. So if someone gives you a critical point, there are really 4 possibilities. It could be a local max, local min, saddle point, or none of the above. So with that, let's do an algebra example where we work on finding critical points for a multivariable function. Let's find all critical points of the following function. F is equal to x cubed plus xy squared plus 3x squared minus 3y squared. So we're going to start off by taking the 2 partial derivatives of f. So f sub x looks like 3x squared plus y squared plus 6x. And f sub y is equal to 2xy minus 6y. So the idea is that we want to figure out where these partial derivatives are either equal to 0 or undefined. So let's start with whatever partial we think is easier. I would say f sub y is easier to work with. And since that's a multivariable polynomial, it's never going to be undefined. So we're just going to set that equal to 0. And actually, most of the time in these type of calculations, typically you're just setting your partial equal to 0. But let's remember that if we're really honoring the definition here, we want to think about which points our partial derivative is going to be 0 or undefined. Okay, so having set that equal to 0, we're going to factor that. So let's factor out 2y. That leaves us with x minus 3. And so there are 2 possibilities, y equals 0 and x equal 3. So really, let's say there are 2 cases here, 2 cases that are going to potentially lead to critical points, y equals 0 and x equal 3. So what we can do is explore each of those cases, and within each case, we'll go back and we'll look at f sub x and figure out what information we can get from looking at that other partial derivative. Okay, so let's label these. Case 1 will be y equals 0. So let's see what y equals 0 forces for f sub x. So f sub x, the more complicated one, would become 3x squared plus 6x. We can now factor the 3x out. That would look like 3x times x plus 2. And again, we want to figure out where this is 0 or undefined. Well, again, since it's a multivariable polynomial, never going to be undefined. So we'll just set that equal to 0, and that's going to lead us to a couple different x values. So x equals 0 and x equal negative 2. All right, now since we're talking about points, it's really best to record these as ordered pairs of x, y. Remember that within case 1, y is equal to 0. So one option would be we've got 0, 0. Another option would be negative 2, 0. So I'm going to put a box around that because that's the end of case 1, and then we'll take a look at case 2. All right, so we got 2 critical points so far. Let's see how many more get added on here by looking at the other case. So case 2 is that x equals 3. And remember that case came from using the information contained in f sub y. So what we need to proceed with the problem is look at what that means for the other partial derivative. So we're going to take x equals 3 and we're going to plug that into f sub x and see what that leads us to. Okay, so f sub x, I think I'll just recopy it from above. It was 3x squared plus y squared plus 6x. Okay, and if we put x equals 3 into this partial derivative, then let's see what f sub x becomes. So just substituting 3 into the x values here, let's see, we'd have 27 plus 18 would give us 45. So we'd have 45 plus y squared. and we're trying to figure out where this is 0 or undefined. So again, because it's a polynomial, it's not going to be undefined. So we're going to set that equal to 0. And in fact, there's no solution. So there's no real y value out there such that 45 plus y squared is going to equal 0. So it turns out there are no critical points coming from case 2. So overall, now we've got our list of critical points. Turns out that there are 2 of them, and I think I'll just summarize them at the end of the problem here. So our critical points, 0, 0, and -2, 0. So just a quick recap for how we handle this type of problem. In order to find your critical points, you need to calculate both your partial derivatives and figure out where they are 0 or undefined. Most of the time, that's just going to mean figuring out where they're equal to 0. So sometimes you'll just be able to factor your 2 partial derivatives independently, but sometimes you run into more complicated situations like this one where you need to deal with one of your partial derivatives first. In that case, I would deal with the simpler one like we did here. We decided f sub y was simpler to deal with. So we dealt with that one first. We produced 2 cases from that, and then we were able, within those 2 cases, to proceed and deal with our second partial derivative and figure out our critical points from there. Thanks for watching.